Hi, welcome to Coursera's Instrumental Analysis. I'm Vicki Colvin. This is Lecture 2 from Week 2. So we just last time talked a little bit about the case study, which is lead in children's toys. And in this Lecture 2, we're going to be touching on sample preparation. Now, sample preparation is the subject of entire books. So what I can only do is a little bit, and each time we kind of delve into a new case study, we'll talk about the sample preparation issues that are particularly unique for that class of atoms, elements, materials, whatever. And in this case, it's kind of no different. What I'm also going to provide you online, but I'm not going to require reading, although it might be interesting for some of you, is actually going to be a book chapter that I found free online. So I think that means I can share it, which really is a nice discussion of sample preparation. I've also got a textbook I've been using on sample preparation. So there's a lot of different resources. And the challenge really is that it really so much depends on exactly your sample, and if it's a rubber ducky or a heart locket, it's going to really affect what you do. But I at least wanted to introduce you to the concepts, because if you're going to be doing analytical chemistry for real in a laboratory, sample preparation is going to take up a huge fraction of your time. The measurement itself is kind of anticlimactic after everything you have to go through to get your samples ready for the measurement. So our goal in sample preparation here is to take a toy, maybe it's a plastic keychain, a metal keychain, I don't know, whatever, a plastic ball, and do some sort of magic that turns it into a clear solution in which the total dissolved solids is very small. The TDS is a very important unit, particularly for mass spectroscopy, but we want a clear solution to our eye. We don't want lots of chunks of material. We have to functionally dissolve things that we don't intuitively think can be dissolved. And for atomic spectroscopies, which are really the bulk of what I'll be talking about, this dissolution really needs to be very complete and very clean in some ways, meaning not leaving behind stuff. For X-ray fluorescence and for neutron activation analysis, which I'll talk less about, it's actually not necessary. For NAA, for example, you go to a nuclear reactor and you put the entire sample in front of a nuclear reactor, and then you can do your measurement. So you need zero sample prep. Although your sample is radioactive for a long time afterwards, potentially. In the other case, if you're going to be using X-ray fluorescence, you might need to mill the surface down, make it really flat, but you don't have to do very much to it. And those are really some of the advantages of what are both of those techniques, which are a little bit less common. Certainly NAA is a research technique. X-ray fluorescence, as you'll see, is much more common, but not something we're going to spend a lot of time on. So I really want to talk about how do you dissolve anything. So this is kind of an outline of the sample preparation process that an analyst usually goes through. Often you have to break your sample down. I mean, honestly, if you drop plastic keychains, no matter how strong the acid is, it can take a long time to dissolve if you haven't already ground up the plastic. So often you're grinding, you're sandpapering, you're doing something to make finer bits of the material that you want to dissolve. That speeds the dissolution process. And you'll see that in some of the case study reading you're doing. Then the really heart of the matter is you got to dissolve. So dissolution is generally preferred because all of the material just basically goes into solution and becomes soluble. Extraction is a process by which you layer another phase on, and the material you want to measure comes out and into that phase. That can be a little bit tricky because you have to know the extraction efficiency in order to really do that analysis quantitatively. So total dissolution is usually preferred, although there are definitely cases where extraction will come in handy. Then you can concentrate it. Let's say you have a very dilute solution of lead. You want to concentrate it so as to make your analysis better. Sometimes you'll do that. We're not going to cover that too much. We'll do that more in chromatography. And then finally, like I said, you make your measurement. By the time you go through all of this, what you have to do to dissolve the sample, though, as I said, the measurement can seem kind of easy. So one thing you can do, and this was kind of the old-fashioned way, is you can do something called dry ashing. So if you want to dissolve your material, one of the things that you're going to be fighting, particularly if you're looking at elements that aren't carbon, hydrogen, oxygen, the organics, those are not the elements. Those are not the elements we're talking about. We're going to be doing organic analysis in the second and the third phase of this class. This is really focused on everything in the periodic. So what you're going to do is you want to get rid of those organics. And one of the best ways to do that is just to combust them in an oven. So you put them in an oven. You might use a platinum crucible or a variety of different crucible materials that are inert, and you heat it up. Often this is good for samples that contain a lot of water. Let's say you're interested in the metal content of plants. This would be an important first step. So you're driving off all the water. You're also making CO2 if you can get the temperature high enough and you can get combustion to occur. So you're basically burning up the sample, and you're going to be left behind with an ash, which contains all your non-volatile components. And that ash you will then dissolve in an acid. So one of the key features of dry ashing, though, is you can't go above about 500 C, because believe it or not, A lot of metals will actually have a vapor pressure, particularly if they're complexed with certain anions. So typically you try to do dry ashing below 500 C, and that can actually lead to very long times. And for some materials, it's just not going to work well at all. But like I said, if you have a lot of water, a lot of organics, this is often your first step. So what's going to be more common in this case study is wet digestion, which is exactly what it sounds like. You're going to put your sample with some really, really nasty acids in a container, and you're going to try to dissolve it that way. So you're going to just throw at it every acid you can think of until it dissolves. Old school, you would do it in an open container, maybe a beaker sitting on a hot plate, of course in a hood because you have acid fumes coming off, and you hope that your sample dissolves in some reasonable period of time. The new school is really to do closed vessels, and we'll talk more about microwave digestion in a second. But some of the common features that I certainly know from experience about wet digestion, you almost always have to heat it. Wet digestion can take a really long time. And so heating, finely dividing your starting material is really helpful. The other thing that's interesting in the acid choice is you don't want to use acids that could precipitate certain metals. So say you have a sample that has a lot of barium in it. Well, if you added sulfuric acid, you're going to precipitate barium sulfate, and that would be a poor choice. You can also sometimes create volatile metals. Chlorides are famous for this. And if chloride complexes to your metals, then you might find even at the relatively low temperatures of the digestion, you'll actually get volatile metals leaving. And that's, of course, a disaster in terms of bias in your measurement. So there's a lot of issues that you have to take into account. And as you're going to see in this case study reading, hydrofluoric acid is a really important acid. You want to stay away from it under almost all conditions. It's a real hassle to work with. But if you've got something that has silica in it, like a glass sample, which is not uncommon, or you have a ceramic sample that isn't going to dissolve easily, sometimes you have to hit it with hydrofluoric acid. The people I know who use HF the most in sample prep are actually geochemists, because you can dissolve almost any rock in the right combination of hydrofluoric and other kinds of strong mineral acids. So the goal is, of course, complete the solution. So how do you choose the acid? Well, here are some of the common cast of characters. A good rule of thumb is you try out a couple of them before you finalize your method. Now, I don't have time to really go into the chemistry behind how these acids work, but I encourage you, if you want to know more, go look at the reading. There's a really great discussion of the ways in which these metals actually dissolve minerals and lots of different elements. And one of the things you can get from that reading is a sort of intuition about, if you're given a sample with a certain composition, what acid should you use first? So I encourage you to look at that. Although in practice, what I would say, I asked around and I kind of know my own experience, most analysts, instead of conceptualizing it in that way, are going to look for a method that describes the sample prep for a type of sample close to the one they have. So for example, if you have to dissolve plastic toys, you're going to go look for some standard published method that describes sample prep for plastic toys. And you're going to just adopt that sample prep or modify it as necessary. So let's get back to the main course material. One of the reasons I'm talking to you about sample preparation isn't so that you have a recipe for every type of material you might face in the future. That's actually really good. If you're in that situation, you can go buy a book for that. But what I did want to do is talk to you about the kinds of issues that complicate the measurement process because of the sample preparation. So when you have to take, let's say, baby teething toys and turn them into clear solution, then there's a ton of things that can mess up the metal concentration you're trying to measure. In other words, there's a bunch of really important sources of systematic error that can very much totally impact your measurement and change the values you're getting. One of the biggest is the volatilization of metals. If you're running an open container digestion, whether it's dry or wet ashing, you have the real possibility of losing metals. And lead is actually very sensitive to volatilization if you heat above about 450 C. The containers themselves can introduce contamination. I actually did analytical chemistry. It was one of my first jobs. I worked in an EPA water analysis lab, and I was the lowest person on the totem pole. So one of my jobs, I got to wash all of the glassware in basically hot sulfuric acid with a little bit of nitric acid mixed in for good measure. And it was scary and a hassle, but the reason we did that is we did trace metals analysis in that lab. And you can get metals sticking actually to the inside of containers, and they can leach out during sample preparation processes. And so it's extremely important, really hardcore analytical chemists are going to be acid washing their glassware all the time because they're trying to get rid of any metals that could potentially contaminate the measurement they're trying to make. Airborne dust, a really good thought is a lot of the methods I'm going to be teaching you this week you need only 10 microliters, less than a drop of material, to get all the information you could ever want. Well, what if in that one drop a piece of dust from the air lands, and that dust happens to contain metals, which in fact dust often does? Well, then you've totally skewed that particular measurement. So as we've gone to smaller and smaller sample volumes, what's happened is the analytical laboratories start to look like clean rooms, like where computer chips are made, where there's no dust at all. And that's actually expensive infrastructure to put into, for example, a company like Toys R Us. And so that's something also to keep in mind, that you can get dust falling into your sample, and that can also really skew your measurements, particularly for small volume applications. And finally, containers can both introduce metals and they can take them out. So containers may bind metals, and that's another thing to keep in mind, that you often run, for example, certified reference materials to evaluate in particular. And the reason that most labs don't do the old school wet digestion anymore is actually the two pictures shown here. One thing I can tell you, you're going to have to do it in a hood because you're heating acid, and those acids make fumes that if you were to inhale would really, really, really hurt you. So instead, you do them in a chemical hood in which the air is drawn away and perhaps goes through scrubbers. But the problem is those hoods are made of metal. So you get a lot of corrosion occurring in the laboratory because of acid fumes coming off of samples. And that's really the problem with open container digestion. Of course, the other problem is just operators. You're handling a lot of acid, it's heating up, there's a vapor. You know, if it gets on your skin, it can really hurt you. So working in a lab on sample prep is perhaps one of the most dangerous things you can do, particularly if you're doing open container wet digestion with, for example, strongly oxidizing acids. So given that, what do we do for real? Can you imagine analytical chemistry labs doing this all the time? Well, many of them do, but what's becoming really popular is microwave digestion. And I just wish it had been around when I was in grad school. So what microwave digestion is, and I give you a couple of links here, and I really encourage you to go and watch the videos. I mean, they're sales videos, but they really give you a sense of how things work. So this is not your mother's microwave oven. So in a microwave digester, what you're going to do is you're going to put the samples in relatively large containers, and you can see in this picture here, those long tubes are actually individual containers, and inside of them are going to be Teflon lined or maybe a polycarbonate container that you put your sample, you put your acids in, and you might let them heat a while, and then you cap it. And when you cap it, you basically create a closed vessel that can increase in pressure if it's heated, but that's okay because that will actually assist in the dissolution process. You then load that thing into the microwave, and that's a cassette that rotates, and the microwave heats it, just like you heat your dinner, except you're not heating to low temperatures. You might be heating to much higher temperatures than, for example, the microwave in your kitchen. And as you do that, the acid heats up like you want it to. It starts to attack and dissolve your samples, but the vapor doesn't go anywhere. It stays in your container. In some cases, it can be vented, and a lot of the really good microwave digesters take the acid fumes away, and they actually scrub them, meaning they put them through a bubbler that has some base in them, so you neutralize them. So you really don't have the impact on the laboratory atmosphere either. They're really slick pieces of equipment, and they're kind of expensive. In any case, you'll see in the methods you read about that microwave digestion has become pretty standard for a lot of the FDA and CPSC analyses that are done, not just of lead, but of other elements. How good is this? So a really typical thing that you're going to do when you have a sample prep is you're going to ask the question, okay, I took my baby toy, I dissolved it in your favorite combination of really nasty acids, and I did a measurement of the metal concentration. How much did I lose in that process? So you do something called a percent recovery experiment, where you take a sample of known concentration of metal and you subject it to the same harsh treatments, and then you measure what you get out. And this table actually reports that for the wet digestion of chocolate, which is our next case study, but I included it here. And what you can see is that most of these elements, depends on the acid, are recovered pretty well. Silver maybe a little bit less, but I want you to look at the table and tell me which elements maybe didn't work so well. You can see, for example, actually lead had some really low numbers there. Another one you'll notice is mercury, particularly with nitric acid. And mercury is famous for being a volatile metal. And so what that means is when you're doing mercury analysis, if you basically heat it at all, it can come off as a vapor, which is bad for your analysis and also bad for you. So one of the things to think about is understanding what metals are you looking for, what metals might be present, because that can impact the way in which you do the measurement. Now, a good solution for volatile metals is, of course, to use a microwave digester, because what you can do in those cases, it's a closed vessel, and you may lose some in your acid fumes depending on how your system is configured. For example, if it's got a pressure relief valve or it's designed to go to pressure. But either way, you have to worry about metals coming off the system, particularly if you vent your acid fumes in some way during the digestion process. But why I include this is to say, actually, wet digestion works pretty well. You don't lose a lot of most metals in that kind of process. There's a couple of other methods of note that I really don't have time to go over in this lecture. We're going to touch on things like solid phase extraction in later lectures, but there's one that's just really cool that I wanted to draw your attention to, and that is the idea of fluxes. This is something that I've actually done a couple of times, and I mention it because it's a common way to make X-ray fluorescence samples. So one of the things that happens in X-ray fluorescence is you can analyze just, your hand. Well, maybe not your hand because there are X-rays, but any surface you could analyze in an X-ray fluorescence experiment. However, one of your challenges is if the surface is rough, then you may not get really good quantitation of the elements that are present. And so often what you do is you dissolve the sample, but you dissolve it in a glass and then you cast it as a disc. It's actually very much like a metallurgy process. And what's really cool is you melt borate salts, and the borate salts become the matrix that holds your sample. The process is called flux fusion, and you can read more about it at the link that I provided. Okay, so let's talk a little bit about the sample prep that's in your case study. So I've given you a couple of different methods. The primary ones are the CPSC methods, and there's one methodology focused on nonmetals and ceramics. And you'll notice the use of hydrofluoric acid when you're dealing with ceramic or glass samples, or what they call siliceous samples. Nonmetals and or things like polymers, they also describe. So you can look at that dissolution, and all of this is microwave digestion, but you should kind of look at exactly what they do. The other one, E1001, is focused on metals. So what if you had a metal keychain or a metal toy like a car or something, use a different process of dissolution and a different sample prep methodology. And the FDA method presents even yet another sample preparation that you might want to look at, because one of the interesting issues is you may have lead in a toy, but is it bioavailable? And so there is some school of thought that says when you do the sample prep, what's called total lead content is not as relevant as leachable lead. And so this FDA method uses a much weaker acid and is really trying to get at that leachable lead number. In this case, it's applied to ceramics, but you can sort of think that through yourself as well. Okay, so we're done with the sample prep lecture. Overall, the goal is you got to dissolve your sample to make a clear solution, and ideally with no floaters in it that you can at least visualize. You need to be thoughtful about your choice of acid. Don't hit it with something like hydrofluoric acid unless you absolutely have to, for example. And if money is available, you should get a microwave digestion apparatus, because that's going to just make the work in the lab a lot safer, a lot cleaner, and a lot more accurate, because you don't have the potential of metals volatilizing. And if you have a sample that for some reason has a ton of polymer or is kind of spongy, has a lot of open space, maybe a lot of water, then you might want to consider something like dry ashing first before doing the wet digestion method. So with that, that's all I wanted to tell you about sample prep. Have fun reading, and I'll see you next time.